Put your forearm next to someone with a very different skin tone. Same room, same sunlight, same species. The difference can look so fundamental that it feels like humans must have always looked like this. But they didn't. Highly pigmented skin is ancestral in our lineage. Much lighter skin evolved later in some populations as humans spent generations living under very different levels of sunlight. But here's where the simple story falls apart. Moving north didn't automatically make humans pale. Ancient DNA shows that some northern Europeans thousands of years ago were still considerably more pigmented than many Europeans living in the same regions today. So what changed, and why did the same human species end up with such different answers?
Put those two forearms under the same light again, the first thing your eye notices is color. But biologically, color may be the least interesting part. Melanin absorbs and scatters ultraviolet radiation, reducing how much of that energy reaches vulnerable tissue deeper in the skin. So instead of thinking of pigmentation as paint, think of it as a filter. More pigment, stronger filtering. And under intense, persistent UV, that filtering could matter a lot. As our lineage lost much of its protective body hair, exposed skin had a new problem to solve. Sunlight was no longer hitting mostly fur, it was hitting us. Human evolution researchers Nina Jablonski and George Chaplin have spent decades studying the relationship between ultraviolet radiation and human pigmentation. Their work makes skin color look less like a fixed human label and more like a biological response to local sunlight. One proposed pressure involves folate. Folate is important for reproduction and early development. Strong UV exposure can interfere with folate-related biology, so greater pigmentation may have helped reduce that pressure. That gives darker pigmentation a much more practical meaning. It was not simply a visual trait, it was part of how exposed human skin dealt with a powerful environment. Skin color was a function before humans turned it into a category. That's easy to forget because modern humans usually encounter skin socially first. We notice complexion, ancestry, identity, labels. An ancestral body didn't encounter a label, it encountered sunlight. And now the obvious answer creates a new problem. If greater pigmentation was so useful, why would any population ever become lighter? Take one person standing under intense tropical sunlight. Now put them on a plane. Hours later, they walk outside into a gray northern winter. Same person, same skin, but the solar environment has changed dramatically. Modern humans can make that journey in a day. Ancient populations could not. For them, a new sunlight environment could remain normal for their children, grandchildren, and thousands of generations after that. At higher latitudes, sunlight strikes the Earth at a lower angle, passes through more atmosphere, and especially during certain parts of the year, less UVB reaches the ground. That matters because UVB helps the skin begin producing vitamin D. Vitamin D helps the body absorb calcium and supports normal bone development. So now sunlight is doing two things at once. Too much UV exposure can cause biological damage, but too little useful UVB can create problems too. Now melanin becomes part of a trade-off. Under strong UV, blocking more can be useful. Under weak UVB, blocking too much of what little is available can make vitamin D production harder. Skin had to balance protection from sunlight with access to sunlight. Think of a window shade. At noon, under brutal sun, pulling the shade down helps. On a dark winter afternoon, that exact same shade might block more light than you want. Same shade, different problem. That's the heart of the Jablonski-Chaplin model. And over many generations, inherited pigmentation differences that worked better in local conditions could become more common. So now the answer feels clean. High UV, more pigmentation. Low UVB, less pigmentation. Mystery solved. Except it's not, because ancient DNA breaks the simple version. Some hunter-gatherers living in Europe thousands of years ago carried combinations of pigmentation-related variants, suggesting substantially darker skin than many Europeans living in those same regions today. Cheddar Man is the famous example. He lived in Britain roughly 10,000 years ago, and genetic reconstruction suggested relatively dark pigmentation along with light eyes. That combination feels unusual mostly because modern Europeans tend to project modern European appearance backward in time. But Europe didn't always look like modern Europe, and that's a huge clue. Latitude can change evolutionary pressure. It doesn't instantly manufacture a finished skin tone. People have histories. People move. Groups meet. They have children together. Gene frequencies change. Diets change. And selection keeps acting while all of that is happening. Later farming populations entering Europe brought ancestry and pigmentation-associated variants that mixed with groups already living there. Some of those variants became more common over time. Diet could change the pressure too. A population getting substantial vitamin D from food is not solving exactly the same problem as one depending more heavily on vitamin D produced in the skin. That's why latitude alone never tells you the whole story. And there's another reason the timeline refuses to stay simple. There was no single moment when a light-skinned gene switched on. Human pigmentation is polygenic. Many genes contribute to melanin production, distribution, and visible skin tone. So don't picture one switch, dark, click, light. Picture several sliders. Move one, then another. Different combinations can produce different outcomes. And here's one of the most interesting parts. Lighter pigmentation didn't evolve through exactly the same genetic route everywhere. European and East Asian populations reached partially similar visible outcomes through substantially different combinations of pigmentation-related variants. Similar environmental problem, different biological routes. So there was never one global moment when dark humans became light humans. Different populations were solving related problems in different ways. That's much closer to what evolution actually looks like. Messy, local, repeated, and full of history. Now, return to a modern group photo. Several people are standing shoulder to shoulder. Their skin tones don't naturally split themselves into two clean biological boxes. There's no line where pigmentation says, this kind of human ends here and another begins there. Humans make the boxes. Bodies give us continua. Overlap, ancestry, migration, mixing, and variation. Our labels are cleaner than our ancestry, and that's where this stops being only a story about ancient sunlight. Pigmentation is biologically real, but the meanings humans later attach to pigmentation can grow much larger than the biological trait. So why did some human populations become much lighter? Because as humans spread into different environments, the balance between UV protection and useful UVB exposure changed. But sunlight was only the pressure. Migration, diet, ancestry, population mixing, selection, and many genes shaped what happened next. That's why the real history doesn't look like a straight arrow from dark to light. It looks like branches, different histories inside the same species. Pigmentation is not the same thing as race. Ancestral doesn't mean primitive. Lighter doesn't mean more evolved. Adaptation is not hierarchy. Different skin doesn't mean different kinds of human. It means the same human species carry different environmental histories forward on its skin. And if that makes the categories feel a little less permanent, leave two words: same species.